Almost there. Well, I guess we can get started. Welcome back, everyone. Does anyone have any questions to start us out or any comments at the moment? Okay, well, for the announcements, this is pretty much it for what we're, let me double check. No, wait, this is pretty much it for what we're doing this week today. It's just going to be 4.4, doing limits through L'Hopital's rule, and the optimization problems in 4.7. Pretty much what's happening in 4.7 is we're looking at the first derivative test and the second derivative test, but they've all been fine-tuned to look for now absolute maximums, absolute minimums, and that's pretty much what we're meaning by optimization. We're going to look at some processes coming from real-world situations and seeing how to optimize a process, minimize cost or maximize area, those kinds of things. But we're going to go back to 4.4 first and just do another limit. And also, because the second derivative test does have its value in optimization, I want to go do one of these problems. The one down here has been put down just for advice, and these problems are still for extra credit. But we'll make this pretty much our warm-up problem. We'll do a second derivative test type problem ahead of the notes on section 4.7 just to get a feel for it, because it's still a very effective test on getting through optimization. Also, if we go forward in the schedule, our third exam is coming up. It's a ways away still, but it's out there. And it's going to end all the way on section 4.7 optimization. So we'll have that little breather week where we'll still do problems so we're not behind. But this is the last homework assignment that will be officially on our third exam. That way I can grade it and give you feedback before we come in for that exam. The sample problems are also posted and same kind of information down below as well. Well, any questions, folks, at all before we get started? Okay, well, let's jump back into the wild world of L'Hopital's rule. If you're curious about L'Hopital, he was a real guy back in the day, a few hundred years ago. And the story goes is that he purchased this rule from someone else. I believe it was Johann Bernoulli, another really big mathematician at the time. And back in the day, these kinds of things were literal secrets. People kept mathematical knowledge hidden because if you knew how to solve a problem, you were an important person. But L'Hopital purchased this rule, wrote a textbook known as one of the first textbooks on calculus analysis, and this is where it showed up. So good on him. He's a good role model. He's releasing information into the world. More of that ought to happen. The idea with L'Hopital's rule is we're looking for two indeterminate forms, 0 over 0, infinity over infinity. We can resolve the fact that they're indeterminate. We don't know what number or symbol should emerge by looking at the rates at which x tends towards a. So we exchange this limit for the limit of the derivatives in numerator and denominator, not doing quotient rule. So we went through a few of these kinds of problems. And one of the things that we noted is it's always important to know if it's even an indeterminate at all. So this one was, and we used L'Hopital, but some of them aren't even indeterminate. I think we had one right down here. This one, we just had to have knowledge of what's happening in the limit. Here, we don't have an indeterminate form. The whole thing was coming out as a 0 overall. The only determinacies are on this list right here. And these are the only time L'Hopital's rule can be applied. So some of them we had to rearrange, like x sine pi over x. It was indeterminate of type infinity times 0, that option right here. But if we put the right thing in the denominator, we got down to the right indeterminate form, 0 over 0. So we just took the derivatives and went from there. This one's pretty tough because it used a lot of weird ideas. This one's also a homework problem with a slightly different format. So a good one to return to. And this is an indeterminate form that we just haven't seen yet. So I felt like we ought to do at least one more question. Here's finally that question. X is going to 0 from the right on the function cosecant x minus 1 over x. And, honestly, plotting cosecant x, it's not too bad, but if you haven't seen trigonometry in a while, that's a mysterious plot to suddenly do out of the blue. So if that kind of question ever came up, I would produce the graph on the actual exam so that we can analyze the situation. And here's what it looks like. Y equals cosecant x. Now, that's a crazy graph, but we only need a certain part of it because we're heading to 0 from the right. So we should restrict our domain on this. Let's just say 0 less than x. And let's go less than 1 because we don't need, or maybe pi or something like that. We don't need the entire graph. So this is what it looks like. And now with that picture there, as x heads towards 0 from the right, anyone see what would happen to just cosecant x? Exactly, we're following this curve. 0 from the right means, well, it's just going to get as large as you would like it by getting as close to 0 as you would like. So you can make that value 10 million if I get close enough to 0. So let's pause here on the graph at least and now go back to the problem. We can say as x tends towards 0 from the right, cosecant of x is tending towards positive infinity. So that's the first thing that happens. Now let's analyze 1 over x. This one is also going to go off to infinity as x tends towards 0 from the right. But again, it's much more clear if we look at the graph of this thing, 1 over x. The reciprocal function, well, just the piece we're interested in, 0 from the right, looks like this. It's also heading off to positive infinity. So we have infinity over, we have infinity minus infinity as our indeterminate form. That's a pretty nasty one. Let's write here, indeterminate, type, infinity minus infinity. If those were actual numbers, real numbers, we'd say it's 0. But here in the land of indeterminate forms, we have no clue what this could turn out. It's always good to take a look at this list, which is also on the top of the notes. And that's the indeterminate form we're looking at right now. Infinity minus infinity. So if cosecant goes to infinity fast enough, this whole thing could be positive infinity. If 1 over x goes to infinity faster, this whole thing could be negative infinity. And it also can compromise and settle down on some real number in between. The only way we're going to get this to work out, though, is we need infinity over infinity or 0 over 0. L'Hopital's rule doesn't deal with this indeterminacy. So first thing to do is we're going to go back here and start fixing the function. Limit as x goes to 0 from the right. And it's hard to really see what to do here, but one hint is if you get infinity over infinity and you even see a single fraction, make everything a fraction and start adding them together. Sometimes that's just the best thing to try to do here. Cosecant can turn into a fraction right away. This is 1 over sine x. Let me make that fraction bar a little bit bigger. We're going to get the least common denominator going as well. Over here, it's 1 minus 1 over x. The slightly longer bar. Now I'm just going to complete the denominators so we have the least common denominator. We can insert x right here. And over here, we're just missing sine x as a factor. So now the limit is now equal to the limit as x is going to 0 from the right of, we don't need parentheses, we can just put one long fraction with x sine x down in the denominator. Cross numerators, it'll be x minus sine x. So we've transformed this limit, which looks nicer, honestly, into this limit, which looks a little bit worse, but it might have the right indeterminate form. So now we need to analyze what happens to this thing. So new set of analysis. Let's go back to where x is heading towards on the limit, and we can write as x tends towards 0, but only from the right. We're only letting x to be positive here. Let's see what happens to the numerator. X minus sine x will converge to 0 minus sine of 0. And that's by continuity. We can just directly substitute in 0 on x minus sine x. We have 0 here, sine of 0 is 0, and 0 minus 0, unlike infinity minus infinity, that one is determinate, it's just 0. Now our hope of hopes is we get 0 down below, but that looks like it would happen. X times sine x goes to 0 in kind of the same way. X sine x will go to 0 times sine 0, but that's just another fancy way of saying 0 altogether. So now we're indeterminate. of type 0 over 0. I'll put an exclamation here because now we can use L'Hopital's rule. So right over here, it's now ready to start being differentiated, the numerator and denominator independently. Well, does that make sense, folks, on how to start this process out? Yeah, go ahead.
So we're not to plug 0 in and do direct substitution, even though it creates a 0 in the denominator, like not just with the 0 over 0, but like with 1 over x on the very first step.
Oh, well, right here. On this one, we really couldn't plug in 0 because we would have had, as x goes to 0 from the right, if we wrote like this, 1 over 0, we would have had just undefined on this thing. And so that's why we had to think of it in this kind of term. 1 over x is really just going off to positive infinity. We can't plug in 0, but we can say over here that it diverges off to positive infinity. But is that's answering the original question you had about that?
Just not like when we did this originally, that really would be small, but close to 0.
Yeah, absolutely. You can plug in anything but 0, and you're getting values that are larger and larger, which is why we're getting the infinity there.
And then kind of like happening like the following stuff.
Down below right here,
Yeah.
right, it's a little bit different only in the sense that on these two right here, I could plug 0 inside x minus sine x, and we got 0 there. We could plug 0 into x times sine x. None of these came out as undefined, but it's the 0 over 0 that's giving us undefined indeterminate. Here, we just couldn't do it with that one thing right here. Same with cosecant x, because 0 can't even be plugged into those functions. The moment we try, we get something like, say, cosecant 0. It doesn't even want to deal with it. So we just looked at the graph of cosecant instead to see where are the values heading towards as we go up to 0 from the right. Other questions or comments about that? Okay, those are great questions. Thanks for asking those. And that's really kind of struggle with this kind of stuff. Limits are happening all over the place. And now once we get to this stage, only because it's 0 over 0, now here's where L'Hopital's rule comes into effect. Let me change colors here just to show what it does. I'll put a H here just as a reminder. That's not required for credit, but it's just a way to say in the notes, this is where I use L'Hopital's rule. We have the limit as x goes to 0 from the right. And we're just differentiating the numerator independent of the denominator. It'll be 1 and minus derivative of a sine will turn into a cosine x. So that fully takes care of the numerator. Down in the denominator, we have to be careful. Anyone see what differentiation rule we need for just that denominator? Exactly, we have to do this the product rule way. So if we differentiate x, we'll get a 1. Copy in sine x. Plus, now copy x. Multiply by the derivative of sine x, that'll give us a negative cosine x. We need parentheses down here just to indicate multiplication because I forgot there'll be a negative right here in the middle. So that's my workaround to make sure I'm really saying multiply. Let's clean up this function a bit and just see what it turns into. Its limit, x goes to 0 from the right of 1 minus cosine x, sine x minus x cosine x. So perfectly good function, but now it needs a whole new analysis. We want to determine, can we plug in 0? That would work if we get something that's not 0 down below. If we get 0 over 0, well, we're back into this land. We have to use L'Hopital's rule once again. So let's take a look. Let me put down a border that kind of goes like this. Okay, we did this analysis only for that function right there. And now we're going to do it again for this function. Let me use an arrow this time to more clearly direct where we're doing that. My right column is just more expansive. We'll say as x tends towards 0 but only using positive values, 0 from the right. Let's see what happens to the numerator. 1 minus cosine x. Here we can directly substitute. Cosine 0 is defined. It'll be 1 minus cosine of 0. Cosine of 0 is a positive one. This is 1 minus 1. So the whole result from the numerator is 0. That's alarming, but if we get like a 5 down below for that one, we should be okay. But with a sine x and x cosine x, looks like 0 over 0 again on this. Let's work it out just to be sure. Sine x minus x cosine x. We're going to 0 from the right. These can be directly substituted again. This will be sine 0 minus, we're plugging 0 right there, so it doesn't matter what happens to cosine at 0 any longer. This whole portion is 0. And the whole thing then equals 0. So that means this is indeterminate. Type 0 over 0 again. So we need L'Hopital's rule again on this function. Let's hope that it finally settles down to something. Let's make this our next step. This will be a L'Hopital's rule step again. So let's put H here just to be clear. We're still heading to 0 from the right. And now we differentiate that numerator. The one here just vanishes because it's a constant. And the derivative of cosine is negative sine times negative 1. So we get positive sine on that derivative. Next, down below, derivative of this sine function gives us cosine. And this is a bit of a pain. A whole new product rule all of a sudden right here. When I do this product rule, I'm going to think of it in this term. I'm going to let the negative x be my first term, cosine x be my second term. And here's how I would differentiate going forward. Differentiate that negative x, and we'll just get negative 1 times cosine x. Next step, copy negative x. I mean, it's really plus negative x, and that's not a bad thing to say because it's reminding us we're using the positive sign in a product rule, which should go there. But if all you put is negative x, that's a good shortcut too as well, if you're just anticipating the negative sign. So I've copied negative x. Now we differentiate that cosine x. It's another negative sine x. And it's a good idea to clean this up because it's just kind of hard to look at, honestly, when it's in this kind of format. So let's say that this is equal to limit as x goes to 0 from the right. Denominator is now cosine x. And hang on, let me look at this a little bit closer. That's clearly a cosine x minus a cosine x, right? That ought to cancel. So we have a cancellation right there first. Then the denominator is just positive x sine x instead. Numerator is sine x as well. And let me double check that just to be sure. I think I did make a mistake here. I'm not happy with, no, we are differentiating it. So sine x turns into cosine x. Product rule here should give us a negative 1 times cosine x. Copy negative x here. Derivative of cosine x is a negative sine x. I feel like we're on the right track. Does that look all right to folks so far? Okay, well, that looks concerning, right? This looks like it's 0 over 0 all over again on this. But the function is changing a good amount. Doesn't look like an infinite loop so far. But let's do our extra analysis on this just to be sure. Oh my goodness, absolutely. I think I just lost my way on this. That's the best way to go for sure. If we didn't do that, probably we're getting into an infinite loop right away. But good call. It's good to always think about the algebra every step of the way. But we would get a value out. We would say positive infinity should be the result then in that case. But we wouldn't have to continue to use L'Hopital's rule. Other questions about that so far? Okay, let me take another look at this work. This one's turning into kind of a monstrous looking problem. It looked friendly at first, cosecant x minus 1 over x, but those infinity minus infinity problems, they turn out to be nastier than normal, I'd say. I feel like I might have a mistake somewhere. Just gonna take another quick look at this work. Product rule right here was sine x, then x here minus cosine x. So sine x minus x cosine x, that looks good. We felt good about the derivative here. Well, I don't think I can spot an error, so let's keep on going. Question here? Definitely is. It'd be a positive cosine x, yes. Oh, that must have been it right there. I took the derivative of sine, no clue why I put in negative. That was the mistake. Thanks for spotting that. That one was completely and utterly invisible to me. That should have been a positive cosine x. So from sine, we get positive cosine x. Let's see how this influences the problem. Here, that would be a positive sign then. All we were doing here is just simplifying the function. Then when we went to take the derivative, let's see what should happen. This positive would have conveyed a positive right here. So we would have taken the derivative of sine, got cosine, plus to plus, derivative of x goes to that one, cosine x copies. This is a positive x, so positive right here. Derivative of cosine becomes negative sine. And then down below here, the cancellation is different. I think this is what saves the problem. I think we're pretty much done at this stage. All due to that one sign being the opposite of what it should have been. Thanks again for spotting that, Danny. That is what definitely saved the problem. So down below, we have cosine x plus cosine x. So that's 2 cosine x. That's why I was getting in trouble. That canceling is getting us into what looks like it's an infinite regress on L'Hopital's rule. This one's minus x sine x. And we have a function that is in fact continuous right at 0. We can plug this in. The end result is going to be now equal to sine 0 in the numerator. Down in the denominator, it's 2 cosine 0. 2 cosine of 0 minus x sine x, that'll be 0 times sine 0. Up in the numerator, the sine of 0 just turns into 0 itself. If we get 0 in the denominator, it's indeterminate and we have to backtrack. But that's what saves it right here. The fact that cosine didn't cancel, 2 cosine 0 is just 2 times 1.
You wouldn't cancel out the signs.
Well, here, if we decide to divide by sine here to here, you would also have to divide by sine right here as well in that location. When it was written before, when it looked like, say, this, all that stuff gone, then Summer was right. Here, you could cancel sine with sine and not have too much trouble in that situation. Sorry, trying to get my, there we go. Control Z doesn't really, oh, it just wants to scroll every time. That's okay. We have 2 times 1 right here. That's a multiplication minus 0. And so the whole entire limit, man, after all of that work, it's 0. As that goes to 0 from the right, you get a 0 out. That's a lot of steps and a lot of analysis in orange that we had to write out to get to there, and a lot of help from the class. Thanks again for finding that sign. I don't think I was ever going to unless I just restarted the whole problem. But when you do a problem like this, not a bad idea to use a really powerful tool just to see, does our work match up with what Desmos would say by a graph? Let's take a look. The function is y equals cosecant x minus 1 over x. We're not interested in the whole graph. We need to be by 0 and only positive values. So 0 less than x less than pi is just fine. And hey, look at that. As we head towards 0 from the right, the values get smaller and smaller and smaller. Looks like they're going to 0. You can't actually put in 0, it's undefined. So that's why we had to do all of that work, because of that undefined right there made it indeterminate. Well, any last questions, folks, on getting through L'Hopital's rule? Okay, what L'Hopital's rule enables us to do is take something that looks intuitive and rigorously prove once and for all, the limit is absolutely zero on that thing. It could have been something else on the graph, really. It could have been, say, 0.000534, and who knows if that's important or not. But let's close off these notes. And now we're going over to section 4.7 on optimization. But first, a quick stop at looking at that second derivative test once again. Any last questions at all, folks, before we close these notes? Okay, let me close this off. So here's the notes we're going to pull in, just the second derivative test. There's a different second derivative test posted right here, so I'm going to put this down below. This one is fine-tuned to only talk about, well, it talks about both, but it also gives you absolute maximums, absolute minimums. But to really get a feel for how this test goes, we ought to do the original first, or excuse me, the original second derivative test. So let's put it right here. We can make this problem be something along the lines of use the second derivative test to find all local maximum and minimum values of the function. Let's say our function this time is, I've got one prepared for us, f of x equals x power 5 minus 5x plus 3. So a nice warm-up problem to start off these notes. And here's how the steps are going to go for second derivative test. I'll use this pencil right here just to organize the steps and the order we take them. So step 1, pretty much you're doing what we did in section 4.1. Find the critical numbers of your original function right here. So let's write out f prime of x. This one's great as a polynomial. These are always the faster derivatives. This becomes 5x power 4 minus 5. And it's done. We have our first derivative. Now, next thing we need to do is set that equal to 0 and solve the thing. To support us on that, let's begin by factoring it maybe first. 5 can be factored out, leaving x power 4 minus 1. And that becomes a difference of squares. This will factor as 5 times x squared plus 1, x squared minus 1. This one's a dangerous one. That one's a sum of squares. We cannot factor it unless we're using complex numbers. So we always leave that one alone. But this one's a difference of squares again. So we can now say we have 5 times x squared plus 1 times x minus 1 times x plus 1. Let me try to fix those x's. They're looking a little deflated. X minus 1 times x plus 1. So that's our first derivative. For finding a critical number, I'd say that's most simplified form. Now let's go for this. Right here in yellow, we need to take the first derivative, set it equal to 0, and solve. We can pretty much just do that right here. Here's f prime. It's now set equal to 0, and we're solving it for our next step. For that factor of 5 right there, you could just eliminate it if you wanted to. You could divide both sides by 5. Now it's gone. I will leave it right there since I want to be reminded that's part of f prime. From this, there is no real number solution that would produce a 0 there. X squared plus 1 is at minimum a positive 1. But you could get a 0 factor here. You could set x to positive 1. And you could make this whole factor 0 by setting x to a negative 1 in that location. So those are immediately our only solutions. And just as a reminder, we could say here, x equals 1, negative 1 are the critical numbers of f. So that's pretty much the very first thing we do. Solve f prime of c equals to 0 or f prime of x equals to 0 to get critical numbers. Now we go to step 2. It is a second derivative test, so we really should be calculating the second derivative next. So here's f prime in the format that's simplest for the next step. For the next step, I'd only want to differentiate that. You can differentiate the factored form, but that's extra complicated for derivatives. That would be a product rule using 1, 2, 3 different factors. So instead, let's go to that format. F double prime of x is going to be 20, x power 3. And the constant of -5 falls off. It just dies and goes to 0. So that's done. That's our step 2. Sometimes step 2 is challenging, especially if you saw some of those extra credit questions. I think the second extra credit question looks like it starts off nice, but then quotient rules start getting involved and it becomes a bit of a longer step. And now finally, here's our step 3. In step 3, we're really just going to write down our conclusions at this stage. We need to grab our critical numbers already specified. And looking at parts A and B, we plug those critical numbers inside the second derivative and analyze its sign. If we have a positive second derivative, you have found a minimum. And for a negative second derivative, you have found a maximum. If this happens, it says the test has failed. That doesn't mean the mathematics was wrong or they didn't prove it correctly. It just means if you get the second derivative coming out of 0, no information can be obtained. There might not be a maximum. There could be a maximum or a minimum or nothing. That's what we mean by the test has failed. You can't get any information out of it. So let's see what happens with our 2 critical numbers right here. Going back to f double prime, I'll just go in order. Let's plug in the first critical number, a positive 1. It's going into the second derivative right above. So this just turns into a 20. But now we can make a conclusion. 20 right here is positive. That's a weird thing to write on paper, but it's not a bad thing to write because it reminds us we're into part A here. I'll put here f at 1. Well, the moment we write f of 1, we have to calculate this and get a value out. So we're going up here to the original function up top. Plug in a 1 and we'll get 1 minus 5. So we're at -4 plus 3. I've lost my place. Let's just do this a little bit slowly. 1 minus 5 plus 3. So we're going to get a -1. Now, once again, that was positive. So we'll say that -1 is a local minimum. So that's what happens to that first critical number right here. I'll put a check just to remind us that we finished that one. We need to do it to every single critical number. We need some conclusion. But does that make sense to folks at the moment on getting that value? Yeah, go ahead.
So if you have to also make it at the first time, just to make sure that they both are greater than 0, or do you just take 1?
What do you mean by calculating the first derivative?
So like plug 1 into f.
Oh, I gotcha. You only have to plug it into f double prime. You could plug it into f prime, but that would just be double checking that you got zeros out, that you really had a critical number. Other questions about that so far? Okay, so let's try this again. We're going to move over to -1. We're still in the step 3 where we're just doing conclusions. So we'll write f double prime at -1. Go to your second derivative function. -1 gets cubed, and that's a negative. So we'll get -20 on this one. So back to part B, we have a negative second derivative at that critical number. So less than 0, and this means f at -1. This one's going to turn into a local maximum, but we still have to calculate it. We're just kind of jumping through hoops on this. Put -1 here, you'll get a -1 when it's raised to an odd power. So turn into a +5 plus 3. So we get 8 minus 1 for a value of 7 is a local max. Then we ran out of critical numbers. I'll check that just to convey we're done with those. And so that means the whole problem ends right at this stage. Any questions at all, folks, on getting through that second derivative test? Okay, the second derivative test and the first derivative test are now trying to do the same things at once. They're finding local minimums, local maximums. There's an important idea behind these. In our optimization section, for some of these problems, it's really up to us to decide what test is the best test to get through. So here's a guidance that might help on deciding that. Let's say here, use the first derivative test if f double prime at x is a hard computation. If it looks like there's a ton of steps involved in there, first derivative test is automatically going to be the better choice. Then we can say, use the second derivative test if f double prime, or excuse me, yes, f double prime of x is an easy computation. Just like what we had here, it's really fast to calculate first derivative, then second derivative. That's a major reason why this is probably the better test for this problem. But let's also put one last comment. Sometimes the second derivative test fails. Let's put that in quotes. It fails in a particular way where in this third case, you just cannot glean any information. If your second derivative is 0, neither positive nor negative. So we'll say sometimes the second derivative test fails, in which case we must use the first derivative test. Whether or not it's going to be easy or not, it'll be the only thing that's left on the table for us to get through the problem. I would say something like this is extremely rare in the optimization section. I believe every problem that I'm going to assign, both the first derivative test and second derivative test will work. So it's our job to find the easiest test and run through it. Not that you have to, but always good advice. With these kinds of problems, if you're doubling your steps because you picked a harder test, for me, I'm like quadrupling my chance of making a simple mistake. Well, that's how second derivative test goes. And like I mentioned, we're modifying this test just a little bit in this section. So here's how it looks originally. It's just trying to find local minimums, local maximums. And here's its modified form. So we still have a second derivative, continuous at what we'll call the critical number c. We still have to find that critical number. So that's just the same as in the first derivative test. Now, this whole line is the original first derivative test. If you have positive, you have a local minimum. But we can say something even stronger now. If the second derivative is not just positive at the critical number, if it's positive for every single value of x, notice we placed x here, not the critical number c, then it has to be an absolute minimum on that one. Likewise, for part B, if the second derivative is always negative, we don't even worry about what happens at the critical number. If we're looking for optimization problems, show that it's always negative, then you have an absolute maximum. So that's how we're running this new test. So it's all about this segment right here. And the fact that this is x, not c. So that's what's making the big modification. We want the second derivative to be either always positive or always negative. That means there's really only going to be one extreme value. There will only be an absolute maximum, also the local maximum, or there's an absolute minimum, which will also be the local minimum. But there wouldn't be both on that function. So that's how that test works. And example 1 is purely a warm-up kind of problem. It's really kind of silly, and some people might already know the trick to get through it, no calculus involved. The reason we're doing example 1 is not all of our problems are so nice. And so we're kind of using this almost like a template to help us with the harder problems down in the notes, which we'll also see in the homework as well. Well, for the homework problems, I also tried to always, for this kind of section, bring in problems to class that are pretty similar to your problems as well. So you can go through the notes to try to match up which one looks right if you need just extra hints on getting through them. But I think we can give this a try. Let's begin with the statement here. The sum of two positive numbers is 15. Immediately, this is what I would write for that information. We need two variables because two objects are being mentioned. Let's let x and y be two positive numbers. Anything that they can give us that reflects a sign, like the value is always positive or is always negative. Sometimes it's pretty important. Other times it might not be super important, but always something to be very attentive to just in case it comes in to play. So next, the sum of those numbers, that would be x plus y, results in a sum of 15. So we're done with that sentence. We can't do anything farther with it. And so now we go to this sentence. It's asking, what is the smallest possible value of their sum of cubes? In other words, we're trying to minimize a function. Let's say that right here. Minimize. In this section, when we say minimize, we're looking for a particular kind of minimum. We're talking about the absolute minimum. I'll often just say minimize or maximize something, but again, we're talking in the absolutes. We're seeking an absolute minimum then in this problem. So we're going to minimize. We need a function, right? You cannot do the second derivative test unless you put a function down. So this is the thing I'm minimizing. F of x equals, and they say sum of, so we're adding things together, cubes, referring to x and y being cubed, so it'd be x cubed plus y cubed, and that's our function to minimize right here. But right out of the gate, this is a very, very big problem for us. I can't even differentiate that function as it stands. I'm not even trying to differentiate implicitly. We want an honest and normal derivative. And if you said you have f at x, and there's a y variable there, that does not go to zero upon differentiation. Y is a true function of x, and we need to unwind it to get through this problem. So let's think of this equation right here as the constraint. Sometimes that's called a constraint equation because no matter what x and y take on as values, they're constrained to have a total sum of 15. We can use a constraint equation to get rid of that y cubed right there. It must be eliminated, so we have an honest function of x only using variables x altogether. If you indicate f of x equals, that has to be our goal. So let's go back to our constraint equation. X plus y equals 15 can be rewritten as y equals 15 minus x. Then we can plug in that value right here for y cubed. And now the function becomes f of x equals x cubed plus 15 minus x cubed. So that's finally a real function of x. If I got to this stage, probably the next thing I would want to do is try to simplify it. But this one is not really worth our effort. The power of 3 here is just going to take a lot of algebra to try to simplify it in this stage. So I'm just going to leave it right as it stands. It's not a hard one to differentiate in that format. So simplifying just doesn't seem valuable any longer. So we did it, folks. We're now on the second derivative test for absolute extreme values. And in the actual homework assignment, there's a couple extra steps for each one of these problems, or really guidance on how these are going to be graded. Each one of these are worth 15 points each. We're doing a problem similar to number 4. And the way those points are distributed is in this way right here. Might be a good idea to just put this into the notes to make it apparent. So on problems 4, 9, 18, and 51, there's no direction where it says you have to use second derivative or you have to use first derivative. It's all up to you. But it's important to know which test you used. So that's what the first thing is here, right here. Just say what test you're using when you're solving the problem. You know, let's maybe put this right here. Probably fits a little bit better. And that's too small. Sorry about that. Let me get that back to there. So first thing I'm going to do in this problem is just say we're using the second derivative test. I mean, we truly are, right? It's right there. We're about to use it for sure. So second derivative test. So that takes care of the first portion. Next, you have to show all steps of that chosen test. And the second derivative test isn't too bad. Let's run through it again. First thing we have to calculate is the first derivative and get a critical number. So that's our step one. So go back to this f of x, and we're going to differentiate it right away. So f prime of x is equal to, first take the derivative of x cubed, we'll get a 3x squared. Next, let's do the derivative of this cubing function with 15 minus x inside. We're dealing with another chain rule on this one. So differentiate 3 first. 3 comes down, the new power is 2. Then multiply by the derivative of that inner function. So 15 minus x goes here and here. That's our inner function. So that's the steps for differentiating this portion here. Does that look right to folks so far? Awesome. So let's carry on. This is now equal to 3x squared plus 3 times 15 minus x power 2. Here, this derivative is not too bad. It's just a -1. And because we're solving an equation this time, now our hand is kind of forced. We should simplify this as much as possible so the equation solving can be done in a clean way. So I guess we're going to square this one out. It's better than cubing it like up here. And we're going to get 3x squared. And I forgot, we have a negative sign, so I'll go minus 3 times. And we're squaring 15 minus x. First, it's 15 by 15, and I think it's 225. I'm not good at squaring those numbers very far beyond 13. Let's double check. Yes, 225. Then it'll be 15 times negative x twice, so we'll get negative 30x. Then the last thing that happens on squaring that is you're taking negative x times negative x, so plus x squared. So all I've done on this step is I've moved the negative sign here out in front, and we FOILed this out. Now let's distribute 3 throughout this whole thing. We get 3x squared minus 225 by 3, that should be 675, plus 90x, minus 3x squared. Then on this step, we have like terms. The x squared is gone. That's going to make equation solving much easier. It's now linear. And it's altogether negative 675 plus 90x. So second derivative test, first step is, well, we have to walk to it by taking first derivative first and then get our critical number out. So we're not done here. Let's set this to 0 and start solving this equation relative to that red dot. We can add 675 to both sides. Divide by 90. Let's get a good value out. In this section homework, we need exact values, but a lot of the numbers divide and give us non-repeating decimals. This one is 675, divide by 90, so we get a value of 7.5. So here's our 7.5. Let's just state here, 7.5 is the critical number. I'll use crit for critical just as a shorthand since we're writing that out quite a lot. So now step 1 is done. And we go to step 2. We need the second derivative. We also need a reminder. We have modified the second derivative into this new format. So let's take a temporary look at it right here as we go to give this a try. So when we're looking for an absolute minimum or an absolute maximum, there is really going to be just one conclusion here. Either your second derivative needs to be proven as positive for all x, or you need to show your second derivative is negative for all x. That's the only way we're getting the absolute values, or excuse me, the absolute minimum or the absolute maximum. So let's take a look at next, the second derivative of f. For f prime of x, you can follow the equalities and just pick a line where it looks easy to calculate. That's where I would calculate it right here. That's our f prime of x. But honestly, a better strategy might be just rewrite f prime of x equals negative 675 plus 90. So now we're not too worried about what we're meaning when we say the first derivative. I just pull it off that line. Calculate the second derivative of x. Oh, I forgot something there. I forgot my x here. That was going to be 0, which would be not good for us. We would have had no conclusion at all on that thing. But now take that second derivative and we get a 90. 90 is positive. So let's use blue here to match up the test. And that's great. This implies immediately through the second derivative test that we've indicated here. Let's take a look. The second derivative had to be positive for all x. That's a constant function. Doesn't matter of your x value. That's always a positive quantity, regardless of what x says. Yes, question first. Sorry, what was the first thing you said?
So when we're verifying x is positive for all x, right? Will always be a constant, and like,
There could be an x, yeah, absolutely. It's possible that right here, your second derivative could be, just like you said, maybe y equals x cubed plus 3. If that was our second derivative as opposed to 90, that's bad. That means it's not positive for all x. So that's a great statement to add right there. Thanks for mentioning that. Here we're lucky because it's 90. We're off the scale on here, but we are in good shape. We're positive for all x's. And if it's something else a little bit nicer, like say x squared plus 1, that would qualify. This is always positive for all x. So if your second derivative runs right here, we would say we have an absolute minimum then in that case. So yeah, that's the things to watch out for. We're lucky it's a constant, easy to analyze, but sometimes it's not easy to analyze. If we can't show it's always positive, then we need a different test. The first derivative test is a little bit more clear for those problems. Well, other questions so far, folks? Okay, so we have positive here, which means we have an absolute minimum. But before we get too far here, let's take a look at what the question even wanted here. It says the sum of two positive numbers is 15. What is the smallest possible value of their sum of cubes? So that's really important. Some of these questions would only want the number 7.5. The wording could have said, what value should x be in order for the sum of cubes to be as small as possible? This time, if they're asking for the value, the end value here is going to be f at the 7.5. So we want the output to the function this time, only because of that word right there. But over here, because we got bigger than 0, we can say there is an absolute maximum. So I would say right here on step 2, on this set of information we took from Moodle, we've done that portion. We've shown all steps of the chosen test. That's where most of the points are right here for 10 points. All we now need to do is state the conclusion. So here's step 3. We want the smallest possible value. So plug 7.5 back into our original function. Sorry, question first? Okay. Oh, thanks for spotting that. That was a minimum right there. That was my mistake on this one. It's not a maximum value. That always kind of messes with my head there. It is a minimum. Thanks for spotting that. Other questions or comments so far? Yeah.
So when you separate, you can really, f of 7.5 equals 15 minus 7.5 plus y, and you solve for y.
You could do it either way. You could either plug it here and here you're 7.5, or like you said, put 7.5 here, you get another 7.5 right here. That's actually the trick of this whole question is you really didn't have to use calculus. You just had to divide this by 2 and you got the right value. The reason we did this problem, which is kind of silly, is it's not too busy of a problem. It's a good way to just to see what does the process look like if there's not too much going on.
So would you start with f of 7.5 equals 7.5?
No, we'd have to put 7.5 here and get a value out.
Oh.
So yeah, we still have to get that value that's being mentioned right here. Other questions or comments so far? Okay, so here's our final step 3. We're just about done with this one. On step 3, we say the minimum sum of cubes is, now we're going back to the original function f, putting in the critical number of 7.5, and then just throwing this all into a calculator. We need our original function f of x. I'll use this one right here by the red dot. And so this will go first 7.5 cubed. Then plus 15 minus 7.5, again, that's just 7.5 again, cubed. And we get this exact figure of 843.75. So that is the minimum value that the question was asking for. So that's the process. If it's a second derivative test, it's really just these 3 steps right here. If we use a first derivative test, we'll really just go back to our section where we did it, mirror those steps, make a conclusion. Only thing that's kind of new is there's a bit of context this time with the problems. Not a whole lot on this one, however. Well, any questions or comments at all, folks, on finishing this one? Okay, well, let's now go off to the next problem and see what's going on with that one. I'll delete this here. It was just put down temporarily. It's still up above on the notes. And here's our new first derivative test. Again, these are very, very similar to the original first derivative test. The only difference is this time it's about absolute extreme values. So when using the first derivative test, we have to have a critical number. So we set the derivative equal to 0 and solve it. And here's what makes it fine-tuned for actual extreme values. If we find that the first derivative is bigger than 0 for all x less than the critical number, and then it goes less than 0 for all x bigger than the critical number, then it's essentially saying right here, you're increasing when there was a positive derivative, then it went decreasing, and it went decreasing across that critical number c. That means you would have an absolute maximum of that function right at f of c. Since we were increasing, right at c it stops, the derivative is 0 for a horizontal tangent line, and then begins decreasing. So part A is just a graph that essentially looks like that. Critical number would be an x-coordinate that produces that horizontal tangent. Then likewise, if we turn it around and say, maybe the derivative is less than 0, you're decreasing here, but this has to be for all x less than that critical number. If it's increasing here, for all x, once again, bigger than the critical number, then f of c is an absolute minimum instead. This one's friendlier than the first derivative. The directions kind of go the way you might expect. There's no weird reversal of directions like on the second derivative test. But this is the hard part. Just like the second derivative test, it also implies for us to find an absolute extreme value, there will be one critical number at all. And we have to prove for all x less than it, it takes on a certain sign. For all x greater than that critical number, the sign flips. Then we'll have one or other of the conclusions. We still need a real number line. We still need to break it up like before, but it's honestly a little bit faster than when we did it way back in section 4.3. Well, for this problem right here, this one's not too bad to get through. I think we have just enough time to do the first portion and calculate the first derivative. Does that sound all right to folks? Differentiate this function and then hit the road. Okay, one more for the road. We won't get through the whole thing, but I think the hardest problem on this one is just differentiating the function. These kind of problems come in 2 sorts of styles. Some of the problems we have to solve are more like this. You have to actually build the function through constraint equations, using the wording to come up with the original function you need. But this problem throws a function right at you. It just starts right away. And for this problem, the first derivative test is definitely the way to go. So I'll put here for step 1, or rather, let me organize these steps a little bit better. Sorry about that. We will use the first derivative test. And honestly, it's a really good idea to use the first derivative test on this one, because if you differentiate that, that's hard already, right? It's a quotient rule. And if you're using the second derivative, you need to use a quotient rule twice. It's extra hard on this, but it's even worse. After you use the second derivative test and you've done two hard derivatives, you have to show that your second derivative is always positive or that it's always negative. That's extremely hard on this kind of problem. Way easier if you have something complicated like this, just hit it with the first derivative test. Great way to start it off. So here's how it starts. We need the derivative of p with respect to I. But maybe before we even calculate that, let's kind of inform ourselves of what is all this stuff. It says the rate in milligrams of carbon per cubic meter per hour at which photosynthesis, so that's why there's a P function here for photosynthesis, takes place for a species of phytoplankton is modeled by this function. We still don't know what I is, but it says I is the light intensity measured in thousands of foot candles. That's a real unit, by the way. I never knew that until I solved this problem. For what light intensity I is PM maximum. So we're trying to maximize, which means the hope is we can do that kind of estimation on the first derivative. But also reading through the context is also saving the problem in a certain sense. I is a measure of light intensity. So that means there is a domain on this. Let's maybe put it right here. I is bigger than or equal to 0. 0 would mean total darkness, and any positive quantity is that intensity in 1,000-foot candles. Light intensity cannot be negative for this kind of function. And that could be pivotal. We never really know until we run through the problem. But now that we've looked at the context, thought about domains, let's differentiate this thing. We need the derivative of 100i. Think of the I as the x in this problem. That's just a constant times x, or I rather. Only the constant would survive when we differentiate the top. Then copy the bottom and multiply it. I squared plus I plus 4 will go minus, and now copy the numerator, 100i. That numerator is going to be multiplied by the derivative of the denominator now. I squared plus I plus 4 turns into 2i plus 1, and the 4 would go away. Then the whole thing is divided by that denominator squared. I squared plus I plus 4. Let's pause right here. Does that look right to folks? So I'm getting through first derivative so far. Questions on this one? Well, one thing we could do to take a look at it is, think of this at 100 as y equals 100x. Always an analogy is a great way to go for these problems because it's just super abstract when we put in weird variables like this. Differentiate your y, and you'd get 100 out. And that's what got thrown in right in that location. Likewise, think of this by analogy as another function, y equals x squared plus x plus 4. If you differentiate that polynomial, you'll get a 2x plus 1. And that's what showed up right here, but now with the variable I instead. So we copied in those locations, and oh, I made a mistake here. Denominator ought to be squared as well. Let's put a power 2 on that. And well, we've got it, folks. That's our first derivative. Well, we know once we get the first derivative, that's never good enough. Not even chapter 3. We still simplified these. And here it's pretty much a requirement. I can't get a critical number in that format until the dust settles on this. So next thing, let's distribute 100 into the group. We get 100i squared plus 100i plus 400. On this group, we'll distribute it inside negative 100i to get negative 200i squared minus 100i. So that's the numerator fully expanded out. Still, it's I squared plus I plus 4 down below, quantity squared. And now we have a cancellation. 100i here combines with the negative 100i, so now those are gone. We're left with, let's take a look, 400 minus 100i squared after combining like terms there. Down below is I squared plus I plus 4 squared. And you know, that's pretty good. That's a simplified derivative. It's not too hard to work with. But because we're using the first derivative test, we need to simplify it even more beyond this point. Now we want the numerator fully factored to make everything go through smoothly. We can start by factoring out 100. That'll leave 4 minus I squared. The whole thing is still divided by, it's tedious to copy this, I know, I squared plus I plus 4. But the minute I stopped copying it, that's where I start making mistakes. I forget if it was even there for sometimes. Finally, we need to factor that one portion, and the first derivative becomes 100. 2 minus I times 2 plus I, division by I squared plus I plus 4, quantity squared. Well, we did it, folks. That's the first step, halfway done. We still need a critical number, but we said we were going to do the first derivative and then call it a night. Any questions at all, folks, on getting through that first derivative? Okay, that's also a reminder of why you probably don't want to use second derivative test on this thing. It's a horrendous experience. It does, well, I'm not even sure if it works because you have to show it's either always positive or always negative. That step could be harder than even the calculus itself. But when we come back on Thursday's class, this is where we're going to end up. We'll carry on this problem and just try to solve as many problems as possible with the rest of our time. Any questions at all then, folks, before we call it a night? Okay, have a great evening, folks, and we'll see you all in Thursday's class.